Hi, my name is Genevieve Bouchard. Welcome back to Vehicle Dynamics series. For episode 5, my colleague Dmitro Yakimenko is here to talk about aerodynamic basics. Hi Dmitro, how are you doing?
Hi Jen, always good, thank you.
In this episode, we will cover key concepts and definitions, aerodynamic drag, aerodynamic downforce, design goal for aerodynamics, aerodynamic package, front wing, rear wing, under tray, testing and validation, and aerodynamic setup. So first, we are getting into key concepts that will later help us understand what is going on with the car. So, Dmitro, could you elaborate a bit about air?
Of course. So air is considered as a fluid, just like water, for example. So it means that it exerts pressure on everything in contact with it, including our race car. Air pressure can be of two types, static and dynamic. Static is the weight of a column of air above, and dynamic is the perpendicular pressure during the motion. Important thing to remember here is that the total pressure, which is static plus dynamic, always remains constant.
Okay, so now what happens when air is moving?
When air is moving, it is called a flow. To represent the flow graphically, we use streamlines that you can see on those pictures. The flow can be laminar or turbulent. Laminar flow is smooth. On the picture, the streamlines don't curl or intersect. The turbulent flow is more chaotic. It creates more resistance when something is moving through it.
And what happens to the flow when it is close to the surface?
So when the flow gets close to the surface, it is called a boundary layer. It is slowed down gradually by the friction with the surface. When the flow flows around the body, it is first attached to it, but then is separated and becomes turbulent, as we can see on the picture on the right. This is called flow separation, and in aerodynamics, we want to avoid that. Next, an important concept to characterize the flow is the Reynolds number. It is density times velocity times length scale of an object and divided by the viscosity of the fluid. What we need to retain is that large Reynolds number, like over 1 million, let's say, it means that the flow is going to be turbulent. If the Reynolds number is small, for example, less than 50,000, the flow will be for sure laminar. In between, it could be laminar or turbulent. So we don't know for sure, and we need to do an experiment to see. Next, the CFD is an acronym which stands for Computational Fluid Dynamics. It is used to study the flow around the car using software simulation. Lastly, the aerodynamic efficiency means how much downforce a car can produce for a given penalty in drag. We will discover these concepts a bit later, but for now we need to retain that we need as much aerodynamic efficiency as we can get.
So what happens when two cars are traveling closely together, like let's say in competition?
So let's imagine this situation and think how the air will flow around the first car. So the first car kind of punches a hole through the air and leaves turbulent wake behind it because of the flow separation, right? So there are two effects on the second car following it. First of all, on a straight, the second car can reach a higher speed. This is called the slipstream. This is because the air behind the first car is pushed away. So behind it, there is less air and therefore less resistance. In a corner, it has quite an opposite effect. It is called the dirty air, which means that the second car has less grip in front tires because there is less air behind the first car.
And how does the air interact with the car?
So now let's get into more details. The airflow creates two forces acting on a car, aerodynamic drag and aerodynamic lift or downforce. First, let's start with drag. It is generated because the car transfers momentum to the air by moving through it and displacing it from its way. Drag is basically the air resisting the car to move, which moves through it. And the goal for a car designer here is to reduce drag as much as possible because it slows basically the car down. There are several factors that affect the drag. First, let's look at the frontal area. As you can imagine, like if we have, for example, a board which flies through the air, it will have much more drag than, for example, a needle, because the board has much more frontal area. So we need to reduce frontal area to reduce drag. Next, the smoothness of the surface also affects it, because let's say a rough surface would have much more friction with the air, so it would have much more drag. Next, the shape of the bodywork also affects the drag. It affects the coefficient of drag, as we call it. Also, the ride height can affect a little bit drag, because the lower ride height, for example, would mean a bit less frontal area, which means a bit less drag. And other important thing is the open wheels. So usually the cars have closed wheels, but in racing cars, wheels are often open, which means that an air is hitting them, and this creates drag because wheels are also rotating. So drag is usually classified into 4 types, and it is based on the way it is generated. So the pictures on the right can help you visualize each type of drag. So first of all, the profile or pressure drag, also sometimes called form drag, it is caused by difference in pressure in front and the back of the car. So this is derived from the constant pressure law we saw in the beginning with static and dynamic pressure. Next, we have the induced drag. This is caused by the trail edge vortices. You can see on the picture, like the rear wing produces the vortices, and this creates drag as well. Next, we have parasite drag. Parasite drag is caused by like bodywork and extrusions in the car, such as, for example, rear view mirrors or, for example, radiators as on the picture. And lastly, we have skin friction drag. This is basically the drag with the surface, with the friction with the surface. As we saw before, like boundary layer is slowed down, and this is due to friction. So this actually creates some drag. All right, next, let's define some more concepts about drag. The main characteristic of a drag is called coefficient of drag. This is determined by the shape of the car, and like different cars would have different coefficients of drag because of their shape. So our goal is to minimize the coefficient of drag for our car. Next, we have coefficient of lift, and coefficient of lift is something we're going to talk about a bit after. Sorry. It is determined by the shape of aerofoil, and the number which characterizes the aerodynamic performance of a given car, like the general characteristic. This is CL divided by CD, which is called the basically lift to drag ratio. It shows how aerodynamically efficient is the shape. And yeah, the more of that, the merrier.
The shape of your car really affects like its aerodynamics. It's like super important.
Yes, as we can see on the pictures on the right with like little yellow shapes. For example, just kind of a circle has the coefficient of 1, which means that we multiply the whole drag equation by 1, right? But if we modify slightly the shape to become more, let's say, streamlined, as we can see on the bottom picture, right? The most bottom part. It has an aerodynamic coefficient of only 1.15. So we multiply our equation by 0.15, which is a lot less, right?
Yeah.
So a lot less drag.
Okay.
All right. Now let's talk about the lift and downforce. So first, we have to understand the lift and how the lift is generated by the wing. First of all, let's define the angle of attack, which is the angle between the wing and the flow. You can see a little scheme on the bottom picture showing the angle of attack. So the principle behind how the wing works is that the air on top of the wing travels a bit faster. So it creates a lower pressure pressure above the wing than there is below the wing. As a consequence, air is from below is pushing the wing up, and this is called the lift. So at a higher angle of attack, which means that the wing is more inclined, there is also like the same principles working, but also there is the air pushed down by the wing. As you can imagine, like a particle of air traveling, it hits the wing and is pushed down by the wing. So this creates a reaction that pushes the wing up, basically. And we have to know that in addition to generating lift, the wing also generates drag because it is a body traveling through the air.
Okay.
And for racing cars, it is all the same thing, but upside down. So basically, lift becomes downforce.
Why is it like that?
It is like that because basically we inverse the wing. So right now, let's say the longer part of the wing is pointing upwards. So like the air above the wing has to travel a bit more. But if you reverse the wing, the air above would have to travel less. So basically the low pressure area would be generated below the wing, and high pressure area would be above the wing, and it would push the wing to the ground.
Okay.
So now more specifically about downforce of a race car. The design goal here for us is to maximize the aerodynamic efficiency, which means that we're producing most downforce and less drag as possible. So to talk about more what are the benefits of the downforce, like why do we even need this? There are two quite simple effects. So first of all, there is an effect on braking. So with the downforce, the car is braking faster, since there is more load on the tires. Like imagine the downforce pushing on the tires, on the car, on the tires. So the tires have more surface contact with the ground, so they have more grip. And thus, the car is braking faster. The same principle applies for the corners. Exactly the same principle, the tires have more grip because of the downforce, and therefore they can generate more lateral loads. And we corner faster.
Mm-hmm. Okay, so now let me summarize a little bit the design goals of aerodynamics. So the first one is to reduce the drag force caused by moving through the air. The other one is to make the flowing air push down on the car so that its tires have more contact patch with the road, thus more grip, so it's more stable.
Yes, exactly. And that makes it go faster. So now let's look at the aerodynamics of a Formula Student car.
Okay, yeah.
So here's an example of an aerodynamic package of a Formula Student car. So aerodynamic package is like a summary term for what we see on the picture. And it consists of three parts: the front wing, rear wing, and the undertray. Now let's look at each of those part components in more detail. So the front wing.
Yeah.
Here the design goal for the front wing is for any kind of wing is to basically maximize the lift, or in our case, the downforce, and minimize the drag of the wing. So the front wing, since it's in the front of the car, it operates in generally in clean air and close to the ground, which gives it additional performance. Like basically it produces a bit more downforce because of that. The surfaces of the front wing are angled to the relative airflow to produce downforce. Basically, these kind of flaps are producing downforce here. Bigger angle of attack of the flaps would give more downforce to the wing, but it would produce more drag as well. The wing directs the airstream up, and the additional benefit of it is that it avoids the rolling tires. So basically the airflow goes over the tires in this case. The purpose of the end plates, we can see on the sides, there are like end plates, vertical end plates. This is to separate the high and low air pressure regions above and below the wing, and to diverge the airstream from the tires. Sometimes, like in our example, there is an opening in the middle which allows the air pass to the under tray, which therefore produces more downforce as well.
Okay. What about the rear wing?
So again, for the rear wing, the design goal is basically the same, is to maximize the lift, or in our case, downforce, and minimize the drag. So the physical principles of the rear wing is somewhat similar to the front wing. Just the additional challenge is that basically the rear wing is located in the rear behind the car. So the designer has to optimize the shape of the body of the car to direct the airflow to the rear wing and make the airflow as laminar as possible at the rear wing. Because as we know, if it is turbulent, it's going to produce less downforce. This comes to the principles of clean and dirty air, where the clean air really gives more downforce. Now moving to the under tray. So here the design goal is to accelerate the flow under the car to produce low pressure there. So the car is pushed into the road by the high pressure air above the car. So we can try to visualize this as the side pod on the picture on the left acts like a wing profile. So basically the whole car acts like a wing, like an aerofoil. So the under tray generates downforce just like a wing, but now the wing profile, as I said, basically the whole car. As we can see, the opening at the rear is larger than in the middle, like in the portion in the middle. So it means that the air would accelerate in the middle of the car and create a low pressure area there. There is now more air pushing on the car from above, so its tires stick better to the ground. The under tray is the part that produces a lot of downforce for a very small penalty in drag, simply because it is under the car, right? Consequently, the under tray produces the same amount of downforce on a high speed or low speed circuit. So independent of how we set up the wings, the under tray produces the same amount of downforce, right? And a critical parameter that affects the amount of downforce produced by an under tray is the ride height in front and rear. So the car line running closer to the ground would generate more downforce because the pressure under the car is even lower due to the tighter space in the middle. The problem can arise, however, if the ride height is changing on the run, which is going to affect the car's aerodynamic balance.
So how do you make the car stable and balanced with aerodynamics?
So to understand aerodynamic balance and stability, let's first understand what is center of pressure. It is basically like center of gravity, but for downforce. It's just the point at which we can consider all the downforce is concentrated at. So for good stability, this point should be kind of behind the center of gravity, if you look at the profile of the car. So the balance, aerodynamic balance, is how much downforce is created on front and rear wheels, because due to the geometry of the car and how it's designed, this amount will not be equal. And it is usually expressed as a percentage. So for example, 64% balance would mean 64% of the downforce goes to front wheels and 54% of the downforce goes to the rear wheels. So the goal here is to keep the balance as constant as possible with the increasing speed, because as we know, the downforce increases with the speed. More speed equals more downforce. But it doesn't mean that it is generated equally on the front and rear tires.
Yeah.
So if you don't keep it constant, and if it changes on the run, for example, the driver might experience sudden shifts from understeer to oversteer, and it may cause the car to spin, and we really don't want we really don't want the car to spin.
Yeah, we want to be in control as much as possible.
Yes, so the aerodynamic balance should be as constant as possible.
Yeah. So how do we test and validate the aero package here at MFE?
So first, for validation in aerodynamics means to generate results with the computational fluid dynamics in simulation, and then repeat the same tests on the real track to compare the both results And ideally, those results should correlate. So how do we achieve this? Is that first we run the CFD model. We load the 3D model of the car into the simulation. And then we run two tests. First of all, we run cornering test. The corner is like 25-meter radius, and we run with 13 meters per second constant velocity. And there is a straight line test with just 20 meters per second constant velocity. So this is done in the simulation, and basically the computer, the software calculates the forces acting on the car. And the amount of downforce from the turning test is determined by the linear potentiometer devices, so simulated, of course. Basically, they measure the difference in ride height as the downforce is pushing down on the car, and by that they can determine the amount of force acting on the car.
So are they doing like a simulation with aero package and without aero package, and they compare the two to see like if it's working well?
So in computational fluid dynamics, we only run with the aero package.
Okay.
And from the CAD simulations, we can get the coefficient of lift and coefficient of drag values, which represent the aerodynamic performance. Now, as we go to the test track then, to test those results. And here we have two tests to do. So first one is the constant velocity test. And this test is done to measure the effect of wings on the downforce while the vehicle is moving with the unchanging velocity. Here there is 3 runs. First one with wings, and then we take them off and run without them. And yeah, the undertray can't be removed from because it's like part of it.
So, like in the simulation on the computers, we don't do with and without aero package, but when we go test like in real, then we try with and without aero package.
Yes, because basically in the simulation we can directly measure the forces, and then we can directly get the CDS and CL. But in real life, we need to measure like the difference the wings produce to. So that's it for the first test. The second test is called coast down test. This test is done to measure the drag force. Like the previous one, the constant velocity test is to find the downforce. This is one to find the drag force. So the car is just set to coast down from a certain speed to determine how fast it slows down with wings and without them. So again, we compare the results with wings and without them to see the difference it makes. And by that we can obtain the basically the difference in drag force, and like that we can obtain the coefficient of drag then. And so ideally, again, these results from the CL and CD from the test should correlate with the CD and CL from the computational fluid dynamics. So now let's move on to our last section, which is on aerodynamic setup. So as we know, the more the angle of attack of the wing, the more downforce and drag it produces. Therefore, it is a task for a racing engineer to find the optimal balance between downforce and drag for each given circuit. And this is called the setup optimization. So as we can see on the pictures on the left, in Monza, which has a lot of straight line, the car runs with the very low angle of attack. Basically, the wing is so tiny that it's almost like it produces very little lift and drag, very little downforce and drag. Sorry. And in Monaco, for example, where the corners are making the most of the track, the downforce, we need a lot of downforce, and the wings are much thicker, and they produce more drag and lift. So returning to Formula Student, we don't have much large variation between like straight line circuits or cornering circuits. So usually we just use the high downforce setup for all of them. However, since the ride height plays a big role in downforce, the suspension some team needs to set up it properly as well. And a common tool to help us with it is Aeromaps. So you can see one on the picture here as an example. So they're generated by the computational fluid dynamics, and aero maps give us insight into how the amount of downforce depends on the ride height in front or at the back. You can see on the x-axis is the front ride height, on the y-axis is rear ride height. And well, aero maps are made for like different situations on the track, namely for braking, corner entry, steady cornering, and corner exit. So we need this distinction because in these situations, the forces acting on the car are a bit different. For example, in the corner entry, we have a deceleration from braking and also lateral force since we already begin to turn in. But for example, in the steady cornering, we only have a lateral force because we only turn with the constant speed. Yeah, so knowing this, we can now do correct setup of the suspension, namely the ride height, to improve the aerodynamic balance and the drivability of the car. So for example, this particular armor is for braking. So only force acting on the car is kind of deceleration. And it relates the downforce of the under tray to the change in front and rear height. So this arrow map is only for under tray. So here the yellow color represents like the most downforce, and like the more the blue color gets, the less downforce we get from the under tray. And so, for example, we can see that if we decrease the ride height in the on x-axis, right? If we decrease it by, let's say, 5 millimeters, and the rear ride height we decrease it by 15 millimeters, which could happen like during braking, for example, then the level curve you get is approximately 1.3, which is like a greenish thing. But let's say if we decrease both ride heights by 15 millimeters, it means that if we take an intersection, it's going to be like in the orange close to yellow zones, and which means it's going to create, the under tray is going to create more downforce. And this is to show that as the ride height decreases equally, it kind of saves us more downforce.
Cool. Thank you so much, Dimitru, for this overview of aerodynamics. I really recommend you guys to go read the book Tune to Win by Kirill Smith and Fundamentals of Motorsports Engineering by Josh Smith. It's really good books to understand basics of aerodynamics and also other topics of the car. Okay, thank you.
Yeah, good luck.